Chapter 9, number 33 deals with a repeating decimal. And one of the things about repeating decimals is that they can always be written as rational numbers, which means one integer divided by another integer. And the reason we can do this is because it can always be written as an infinite geometric series. So we'll show you how to do this here. So our number is 0.12121212 dot dot dot. Now on a calculator, what you can do is if you just write it in enough 1-2s, you can do the math frac trick, and at least that'll tell you what the answer should be. And your calculator should be able to tell you that this ends up being 4 over 33. So at least we know what we're aiming for here. 4 over 33. I'll just put that over here so we have it. Okay. The trick to writing this as a geometric series is to break this up into the repeating chunks, right? So that first 12, that's really 12 over 100, right? So you could write it like this. And then I've got to add the next 12 to it, but it's really 0.0012 that I have to add to it. And 0.0012 is the same thing as 12 over 10,000. And then the next 12 right here is what I would add in next, and that's really 12 millionths. I'll put the commas so it's easier to see. The next one is going to be another 12 over, what's that, 100 million. So I'm just going to do dot 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 here. Now, if I write this way, 12 times 1/100th plus 12 now, oh, whoops. 12 times. Now, 1/100th squared is 1/10,000th. So I can square that now. I've got 12 times 1/100th cubed at this point, and it just keeps going from there. Okay, so there's my geometric series. Now, in this case, this is my first term, A1, which in this form up here, it's just A. And this is my A1 times R, A1 R squared, right? So you got to be a little bit careful because notice the R is part of this first term. So let's see. Now I'm going to use this trick where we do the. I'm going to rewrite this first. 1 over 100. We'll do this the quote unquote long way, even though it's not really that long. It's a simple idea. So the trick is multiply the entire sum by the common ratio. And so instead of this first term here, 12 times 1 over 100, I multiply by another 1 over 100, and I get 12 times 1 over 100 squared. And then I take the next term here, and I multiply by 1 over 100, and I get this term, 1 over 100 cubed. And I just keep going, and I get all the rest of the terms in the infinite series. So if I subtract one from the other, I get 99 over 100 s equals the first term minus 0, which is 12 1 over 100, plus, and then these all cancel, and so do all the rest of the infinite terms. So that's really all I get, 12 over 100. So then s ends up being 12 over 100 divided by 99 over 100, which ends up being 12 over 99, which ends up being 4 over 33. Now, you could also do this thinking of it in terms of a plus ar plus ar squared plus dot dot dot. And a in this case is my first term, 12 times 1 over 100. I'm trying to write it like the problem has it up here, right? A plus ar squared. And if we use the same exact trick where I multiply by r, then I'm going to get ar plus ar squared plus, and so on. And when I subtract, I'm going to get s times 1 minus r, if I factor out the s minus rs. And then I get a, and everything else cancels. So then I'm left with s equals a over 1 minus r. And if you think about what that equals, well, a is 12, not just 12, The 12 times 1 over 100, remember. And 1 minus r is 1 over 100. And now I've got 12 over 100 divided by 99 over 100, which was the same thing that I had right here anyway. Well, right there, really. Okay, and this, remember, maybe we haven't gotten to this yet in class, but that is the sum of an infinite geometric series. And remember, this only works if r is between 1 and -1. If r is not between those two values, then the series explodes, it doesn't converge, it diverges. Okay, hope that helps.